Hello, this is Mrs. Sargent, and this is lesson 8.1, Solutions and the Dissolving Process. So a solution is essentially a homogeneous mixture. And it is the same throughout. We can't see the different parts of the mixture because it is evenly mixed or uniform. There are two parts to a solution. There is a solute and a solvent. So here I have a diagram of a solution, and that solution is equal to the solute plus the solvent. In our picture, the solute is shown with the orange dots, and the solvent is the blue. So the solute is the substance that gets dissolved in solution, and the solvent is the substance that dissolves the solute. If you look here in our diagram, there is a smaller amount of solute and a larger amount of solvent. I can't, right? So in this lesson, the vocabulary is going to be very important. We've already talked about 3 different words that start with sol. So we need to be able to keep how we define them straight. So make sure you study the vocabulary. If you need to make flashcards, you can do that. But this vocabulary will be important for the rest of our unit. So you want to make sure you have an understanding of it at this point. So here's a couple solutions that we can take a look at. Our first solution is Kool-Aid. Think about, what is the solute in Kool-Aid? Well, it's the flavoring packet, which has the flavoring, the dye, but it's mainly sugar. The solvent, we mix that flavoring packet, the mix of the Kool-Aid, into water. So that is the solvent. We have less of the flavoring, more of the water. Another solution is the air in our atmosphere. Air is 78% nitrogen, 21% oxygen, and 1% argon. So take a look here. What has the smaller amount in air? Well, it's oxygen and argon. So our solute is going to be oxygen and argon. Our larger amount is nitrogen, and so that is going to be our solvent. So solutions can be solids, liquids, or gases. So here's a couple examples. We can dissolve a gas into a liquid. An example of this is soda. If you have a can of soda or a bottle of pop, there is, when you open it, it fizzes, and that fizz is CO2. That is the gas that is dissolved in the essentially sugar water. That's the other part of your soda. If you've ever seen this Soda Stream, you can buy the sugar water or the flavoring, and then you have a CO2 cartridge and you're dissolving the CO2 into that flavored water to get the carbonation for the soda that you make at home. A solid and a liquid. An example of this would be seawater. So the solid that is dissolved is the salt, and the liquid is water. And then a liquid and a liquid. I think that this is one that seems to be a little bit harder for me to think of examples for. But vinegar, the smell of vinegar is responsible for it is acetic acid. And it is dissolved in water. And then a solid and a solid, the metal alloys, we talked about these at the beginning of the year. It's a mixture of two different types of metals. So example of that is brass. This is a mixture of copper and zinc. You start with two solids. You do have to heat it up in order to evenly mix them. But you start with two solids and you end with another solid. So it is important to note that some chemicals will mix into solutions and some will not. But if we look back here at these examples of different types of solutions and different states of matter, 3 of these involved water. Water is known as the universal solvent. Not everything will dissolve in water, but a lot of things will. And so it's referred to as the universal solvent. But you can dissolve stuff in things other than water, and not everything will dissolve in water. So soluble and insoluble. A soluble is a solute that dissolves in the solvent. Insoluble, the solute does not dissolve in the solvent. These terms are referring to both solids and gases in liquid. So if it dissolves, it's soluble. If it does not, it is insoluble. Miscible and immiscible refers to a liquid in a liquid. So here, miscible is liquids that do dissolve in each other. Immiscible is liquids that do not dissolve in each other. We have oil and water, and no matter how many times I stir this, these two are not going to evenly mix. They're going to eventually settle back out into the two different layers. Because oil is immiscible in water, this helps us clean up oil spills in the ocean because we can pull the oil off of the top of the water. Now that oil is dangerous to our wildlife and to our environment, and so that's why we want to get it cleaned up, but the water and the oil are not going to mix because they are immiscible. Solvation is the process of dissolving a solute into solution. So we have a salt, which is sodium chloride, that's table salt, And then glucose is C6H12O6. Take a look at these and identify which one is covalent and which one is ionic. Well, sodium chloride. Sodium is a metal, chlorine is a nonmetal. So that metal indicates that this salt is an ionic compound. Carbon, hydrogen, and oxygen are all nonmetals. So there is no metal. So this is a covalent compound. Now there is different processes for ionic compounds to dissolve and covalent compounds, and we're going to talk about those, that solvation or the dissolving process. So, ionic compounds. Before you write anything down, just take a look at these pictures. We have a sodium ion here, which is positively charged. And then we have chlorine, which is negatively charged. Those are the two ions that are involved in sodium chloride. Okay, sodium is our cation because it's positive, and chlorine is our negative ion because it and an anion. Now water, there is a positive and a negative end to water. So we have our water molecule, we have the oxygen bonded to two hydrogen, and if we think back to our covalent bonding unit, when we talked about Lewis structures, we determined the polarity of some of our different compounds. The electronegativity of oxygen is greater than hydrogen, so it's going to pull the electrons towards it. So that's going to make our oxygen partially negative and our hydrogens partially positive. So the opposites attract. A positive is going to attract a negative. So our positive ion is going to attract the oxygen end of water, the negative side. Our chlorine, which is negatively charged, is going to attract the positive end of water. So the positive end of water is attracted to the anions, the negative ion. That positive end of water, again, is the hydrogen end. The negative end of water is attracted to the cations, the positive ion. The negative end of water is the oxygen end. Once the water molecules have surrounded the ions, it carries the ions into solution. This is the process for your ionic compounds. They are going to separate. The ions are going to separate and then dissolve following those three steps that we talked about. It is important to note that not all salts are soluble in water. The ionic bond between the ions may be stronger than water molecules can overcome. These are insoluble salts. So if I gave you an example of a compound and I said that you try to dissolve it in water, and no matter what you did, it would not dissolve, you just need to know that that would be known as an insoluble salt. So for covalent compounds, they follow a different dissolving process. The rule like dissolves like is going to determine if a covalent compound will dissolve or not. So polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. So the polarity needs to be the same in order for the solute to dissolve in the solvent. So if we think about water, again, here is our Lewis structure for water. And we need to determine, is water polar or nonpolar? Well, if you take a look at the back of your periodic table and that chart that we have for our molecular shapes, we first need to determine how many atoms we have. Well, we have hydrogen, oxygen, and hydrogen. So we have 3 atoms. And then we need to look and see how many lone pairs are on our center atom. Well, these dots represent electrons, and there's 1 pair here and another pair there. So we have 2 lone pairs on the center atom. And then we have 2 bonding areas. And so you should see that that gives you a bent shape. Well, bent is a polar molecule. So water is polar. So here we have a sugar crystal, and the molecules of sugar are breaking off and the water molecules are surrounding it. So we know that water is polar. So what does our sugar molecule need to? Well, sugar has to be polar in order to be dissolved in solution. Here we have a glass of water with oil, and they are separated into 2 different layers. So the oil is not dissolving in the water. Well, we know water is polar. Oil is nonpolar, and that's what's causing it to not dissolve in water. You might need to take a look back at Unit 4 and the polarity lesson if you need more help with determining the polarity of some of your molecules. Or come see me and ask questions. Electrolyte versus non-electrolyte. What do you think about when you hear electrolyte? You might think about Gatorade. Well, if you just look at electro, you might think about electricity. Well, electricity current flows among charges. So, did an ionic or covalent compound produce charges? Well, ionic compounds separate into ions that give us those charges. So our electrolytes are going to be ionic compounds. Non-electrolytes are going to be covalent compounds. So compounds that conduct electricity when dissolved in water are electrolytes. Non-electrolytes are compounds that do not conduct electricity when dissolved in water. And here's just a comic to help you think about the like dissolves like rule. One bear says the other, help, help, I'm dissolving. The other bear says, but bears are insoluble. And the First pair says that's easy for you to say. You're not polar. Go ahead and work through the practice on the following page. You need to make sure that you understand that vocabulary again and then can apply it to different chemicals and scenarios. Thanks for stopping by. Come and see me if you have any questions. Thanks. Have a good night.